Okay, so this video is on inverse functions. Inverse functions should be familiar to you from the Unit 1 and 2 course, but it's really important, it's really easy to have a 3-mark inverse function question and you actually not earn any of the marks through poor setting out or poor notation. So it's really important to get this right, okay? So the key thing is that if a function is one-to-one, then it has an inverse function, okay? If a function isn't one-to-one, if it's a many-to-one function, it does still have an inverse. It is just that the inverse is not a function, okay? So in order for it to have an inverse function, the original function must be one-to-one. We'll come back to that when we talk about the graphical implications. The inverse function of f is denoted by f to the power of -1. Okay, now it's a really misleading notation that I don't like at all, because we all know that x to the power of -1 means 1 on x, but f to the power of -1 of x does not mean 1 on f of x. Okay, it's not the same thing at all. We've seen this notation before. We've seen this notation in our inverse trig functions. Inverse sine, inverse cos, and inverse tan are sine to the -1, cos to the -1, and tan to the -1. Okay. And that's exactly what they mean. They don't mean 1 divided by sine. They mean the inverse of sine, the opposite function to sine. So yeah, it's a slightly misleading notation, but making sure that we're using it correctly. So, to obtain the rule of an inverse function, we're going to let y equal f of x. If there is no y in the problem, before you can make a statement about swapping x and y, we need to have introduced y to the problem. We're going to swap x and y, and we need to be careful about how we write that line. Okay. For example, you cannot just have a maths that goes from y equals x squared to x equals y squared with no statement in between here. Okay. Because this is not a valid mathematical step. The second equation is not equivalent to the previous equation, so you must be making some kind of statement in between there. Swap x and y for inverse. Write the words. Okay. In recent years, I've actually taken to combining these first two steps together and straight away saying, let x equal f of y. Okay, so you've introduced your y into the problem and you've swapped x and y at the same time. Okay, and then you want to rearrange to make y the subject, and then you want to answer the question. Let's just talk about why that's happening. So the simplest thing is we're trying to create an inverse function. That is a function that does the opposite steps of the original function. So for example, if our original function was x plus 5, the inverse would be x minus 5. We want to do the opposite operations in the reverse order. If the original function was 2 times x minus 1, we would want our inverse function would need to be x plus 1 and then divided by 2. The opposite of those things in the reverse order. If our original function is x squared, our inverse function is going to be root x, but there is some domain issue that we need to be careful of there. So what we're trying to think about is, well, algebraically, how do we get from here to here? If we want to generate the inverse operations, we want to undo everything that's happening to x. Essentially what we want to do is kind of make x the subject, so we want to take away 5 from both sides, okay? But then we're creating a new function which is doing all those opposite things, okay? So we swap x and y around, so we get, x equals y plus 5, and then when we make y the subject, we're generating all of those inverse operations, okay? Again, just notational things. So the process by which we can generate all the inverse operations is if we switch x and y and then rearrange to make y the subject. In that process, we're generating all of those inverse operations in the reverse order. So we make y the subject, and then the final step, which is where you will lose most of your marks, is to make sure that you answer the question. If the question asks you for the inverse function, your answer should be f to the -1 of x is equal to something, and the domain of f to the -1 is something. Okay? A function is defined by domain and rule, and quite often with an inverse function, the domain is not the implied domain, and so therefore you must really be explicit about making sure you've written it. The question will usually ask you for both, but even if it doesn't, if it asks you for the inverse function, and the domain of that inverse function is not the implied domain, you must state the domain. If it's a restricted domain, it must be stated. Otherwise, the implied domain is assumed, and therefore your answer is not correct. So rule and domain with valid correct notation. Please can we write that the domain, it's the domain of the inverse that equals this, because you've now got two functions in your problem. Don't just write that domain equals this. Is that the domain of f or the domain of the inverse? Be clear about which function's domain you are talking about. Okay. Now, remember what we've done in this process is we've swapped our x and y values. So the domain of our inverse function ends up being equal to the range of the original function, and the range of the inverse function is equal to the domain of the original function, because you're swapping around the x's and y's. Everything that applied to x now applies to y, and vice versa. An inverse function is only fully defined if its domain is given. I've talked about that. That's about making sure that you state the domain, even if it's not asked for, particularly if it's not an implied domain. Graphically, the inverse function is a reflection of the original function in the line y equals x. And that's just what happens if we swap the coordinates. So if you have the line y equals x, and you have the point 3, 1, for example, when you reverse its coordinates and make it 1, 3, it's now going to be up here. And graphically what's happening is it's the mirror image in that line y equals x. Okay, so it's going to be mirrored over that line y equals x. So if we do that to an entire function, not just a point, we flip it in the line y equals x. So if we have a curve going this way, when we flip it in the line y equals x, it's now going to go this way. So that every single point has been mirrored over that line. Okay? So, sometimes there's quite a bit of geometry in being able to think through that shape correctly. Consider maybe folding your paper in half down the line y, just making a fold in your paper down the line y equals x to check if the drawing that you've got is actually symmetric about that line. Okay, so graphically, actually I'm going to leave that drawing to illustrate the next point. So as I said, let's say we've got the line y equals x, okay, and we had a curve going this way. Its inverse would be a curve going this way. So graphically, the inverse, I've said that. So the next point is f of f to the negative 1 of x. Okay, so if this is y equals f to the negative 1 of x, and this is y equals f of x, and you take this function and sub it into this function, so that you are doing f of f to the negative 1 of x, or if you did that in reverse, it would also be the same to do to sub the original function into the inverse function. What you're doing is you're solving them simultaneously. And when you solve the two equations simultaneously, graphically, you're finding the points where they intersect. Now, if it's a inverse function, the graphs should intersect on the line y equals x. Okay, so f to the negative f, when you sub the inverse into the original, or if you sub the original into the inverse, you should just get x. Okay. Now, there's a slightly misleading statement to assume that a function and its inverse always intersect on the line y equals x. For the vast majority of functions, and in fact this process assumes that they do, for the vast majority of functions they will, but it is possible to get functions, for example, now let me see if I can generate one. Let's have a think about the cubic is the simplest one, I think, from memory. No, negative cubic, this one goes this way. There's y equals x. If I mirror that graph in the line y equals x, they're definitely going to intersect at that point. It'll still go through that point. So any points on the line y equals x will still be points on the inverse function. But when I mirror it, this graph is going to come up here. So it's going to do that. And this is going to do that. And so we do get one point of intersection on the line y equals x, but we actually get two others that aren't on the line y equals x. So if you're trying to find where a function and its inverse intersects, please be careful about how you do it. Please be careful about assuming that it will be on the line y equals x. Okay, so I tend to, if I'm trying to find the points where two graphs intersect, you could obviously solve. You could obviously solve f of x equals inverse f of x, but usually that's the most complicated equation to solve. So I would generally encourage you to solve the original function equals x, because that's going to give you all the points where they intersect on the line y equals x. And that works most of the time, but you do just need to think about your graph shape, because if your graphs are going to intersect somewhere not on y equals x, and if they do, it'll generally be on y equals negative x, or an equivalent to that, in line with the gradient of -1, you need to actually solve the function equal to its inverse, okay? But it's really just about thinking a bit about the graph before you work out what equation you need to solve. Okay, so graphically, this statement means that the functions y equals f of x and y equals the inverse of f of x will intersect on the line y equals x. Now, many people sometimes use this idea for calculating an inverse function. Personally, I still stick to this. I find, for all intents and purposes of what we're doing, it works. I find it's more intuitive to understand what's happening for many students. But it is possible to use this idea, and I'll talk that through when we have a look at some examples. To find an inverse using CAS, there's no special instruction to get your CAS to find the inverse. You just need to talk it through the algebraic instructions. So define your function and solve f of y equals x for y. Sometimes quite often it can give you quite unhelpful algebraic versions of the answer, and I generally find that finding an inverse function is quicker and easier to do by hand. Okay, let's have a look at some examples. Consider the function f with a restricted domain from 2 to infinity, where f of x is equal to 1 on x minus 2. Find f to the -1, the inverse of f. Okay. Alright, so we want to think about introducing y and swapping x and y. So I'm going to let x equal f of y. And that's doing those two things all at once. So x is going to be 1 on y minus 2. And now I want to rearrange to make y the subject. So I'm going to multiply by y minus 2 equals 1. I'm going to divide by x. Y minus 2, you can do that in one step. Y minus 2 equals 1 on x. And I'm going to add 2. Y equals 1 on x plus 2. Now we're nowhere near finishing. Okay, this question might be, if this question's only worth 2 marks, you haven't earned either of the 2 marks at this point. If this question's worth 3 marks, you've earned one of the 3 marks, apologies. So you need to answer the question. So therefore, our inverse function, f to the -1 of x, is equal to 1 on x plus 2. And it's a function which isn't fully defined without its domain. And because the domain of the original was restricted, the range of this is restricted, and therefore that means that its domain should be restricted as well. Okay, so let's think about what this original graph looks like. It's a hyperbola translated to the right by 2, but we're only looking at it where the domain is from 2 to infinity, so we're only looking at that part there. So we know that the range of f is actually just from 0 to infinity, or we can call that r plus. Okay, and so that is equal to the domain of the inverse, which is just going to be r plus. So when we look at this hyperbola, which is the hyperbola translated up by 2, we're not going to have both parts. We're only going to have the part where the domain is r plus. Okay, we're not going to have this part down over here. Calculate the points of intersection between the function and its inverse, and sketch the graphs of the function and its inverse on the same set of axes. Okay, I'm going to do those things in reverse. So we've just done 2 rough sketches of what the graph and its inverse look like. Okay, it's really important when you draw a function and its inverse on the same set of axes that you use a square scale. That is, you use the same scale on the x and the y axes, because it will help you to make sure that it'll help you to see that mirror image in the line y equals x better. Okay, your y equals x will be at a perfect 45-degree angle. You'll have, in this case, I'll draw them in 2 different colours. So our original graph had an asymptote at x equals 2, and we were just looking at this part here. Okay, and then our inverse function, so this is y equals f of x. Our inverse function had an asymptote, so it's a hyperbola translated up by 2, so those asymptotes should intersect on that line y equals x. Okay, your graphs should intersect on the line y equals x as well. So when I draw in this graph, let's try that again. I want to make sure that they're actually meeting on that line y equals x. So this is the inverse. Okay, and that is x equals, sorry, that's y equals 2. Sorry, it's a slightly crooked asymptote there. So if we want to find the points of intersection, we can see, having thought through what the graphs are doing here, that they only have one point of intersection, and it is on the line y equals x. So there are 3 points intersecting, 3 lines, sorry, intersecting at this red point. Y equals f of x, y equals f to the negative 1 of x, and y equals x. So you can solve any combination of those 3 lines to find the point of intersection. Okay. I would always advocate, if it is an option, that the easiest equation to solve is going to be f of x equals x. F of x equals f to the negative 1 of x will always be the most complicated equation to solve. Something equal to x will be the simplest equation to solve, and I would always encourage you to use the original function equal to x, just in case you made a mistake when you found the inverse. So our original function is 1 on x minus 2, and that's going to equal x. So we're multiplying both sides by x minus 2. Let's expand out that right hand side, x squared minus 2x. Let's make one side 0. Factors of negative 1 that add up to negative 2, they don't exist, so we're going to need quadratic formula to solve this. Negative b, so that's negative negative 2, positive 2, plus or minus the square root of b squared, which is 4, minus 4 times a, which is 1, and times c, which is negative 1, all over 2a. So we're going to have 2 plus or minus the square root of 4, negative 4 times negative 1, so it's going to be 4 plus 4. So we've got 2 plus or minus root 8 over 2. Root 8 is 2 root 2, simplifying your surds. And then simplifying your fraction, we can divide everything there by 2 to get 1 plus or minus root 2. Now, remember our domain. We know that x has to be bigger than 2. We can see they intersect past that asymptote. And f of x, that's the domain for f of x, and so therefore x has to be 1 plus root 2. Okay. Now the other advantage is that's the x coordinate of the point of intersection, but what we've got to remember is, so 1 plus root 2, is that it's on the line y equals x, so the y coordinate will be the same as the x coordinate. So once you've found your x coordinate, you've got your y coordinate, so that means that y is also 1 plus root 2, and so therefore your point of intersection is 1 plus root 2, 1 plus root 2. Let's check that we've answered the question. Sorry. So calculate the points of intersection, so there's only one point, that should technically say that. Calculate the points of intersection between the function and its inverse, and sketch the graphs of the function and its inverse on the same set of axes. Okay, so we've done that. Alright, example 2. Consider G, where G has domain R and rule G of x equals negative x cubed. This is the example I gave to you before. Find the coordinates of the points of intersection between G and the inverse of G. Okay, so we want to think a little bit about, and this is where I'd always encourage you, one of my students asked this in class the other day, do you think we should draw a graph? And yes, even if it doesn't ask for a graph, what is happening here? It helps you visualize it and see it to know what you're going to need to do or what you might need to be careful about. So G of x is a reflected cubic, so it looks like that. And so without even calculating the inverse of G, just trying to think through what the reflection will be, it's going to be going this way instead. So we're going to get 3 points of intersection. Okay. So we're going to actually need to calculate the original function equal to the inverse, or actually we could recognise that these are going to be on the line y equals negative x and solve that instead. It's up to you. Okay. Alright, so let's find the inverse of G first, and we'll use that. That will be the more traditional way to do it. So let x equal G of y, which means that x equals negative y cubed, which means that negative x equals y cubed, which means that y is the cube root of negative x, which it's worth noting is the same as the negative cube root of x, because if we cube root a negative, we still get a negative. You might choose to write that as negative x to the power of a third instead of writing the cube root, however you want to write it. Okay. So your inverse of G is negative x to the power of a third. Now, I've drawn that graph too big because I'm going off room here. Let me make that smaller. Okay, so let's find our points of intersection by, rather than looking at when x equals negative x cubed, because that's only going to give us this one, we'll instead make g of x equal inverse g of x. So that's going to be negative x cubed equals negative x to the power of a third. Okay, so we've got negatives on both sides, so that's x cubed equals x to the third. Why don't we try cubing both sides? So if we do this, we're going to have x to the power of 9, we multiply powers in that situation, equals x to the power of 1. So that's x to the 9 minus x equals 0. X is a common factor there. X to the 8 minus 1 equals 0. And we get null factor law tells us we get x equals 0 or x to the 8 minus 1 equals 0. So x to the 8 equals 1. Now the 8th root of 1 will be plus minus 1 because it's an even root. So those points of intersection are going to be at plus minus 1. And then you're going to need to substitute back in. So obviously when x equals 1, y will be negative 1. When x equals negative 1, y will be positive 1. So we're subbing back into your original function. And obviously 0, 0 are our 3 points of intersection. So therefore we're going to have negative 1, 1, 0, 0, and 1, negative 1 are our 3 points of intersection between those two graphs. If you just solve g of x equals x, you only would have found this one. Okay, so do think a bit graphically about what's happening so you can know whether you can just solve g of x equals x or whether you need to solve g of x equals the inverse of g of x. Okay. Before we move on to the bit trickier ones, I'm just going to go back and talk about that alternative method up here that I did mean to talk about earlier. Instead of letting f of x equals f of y and rearranging to make y the subject, what you can instead do is use the fact that f of inverse f equals x when we have inverse functions. And so what you do is, remember f of x in this case is 1 on x minus 2, okay? So f of the inverse is replacing all of the x's with inverse f, okay? So this is 1 on inverse f of x minus 2 equals x. And you can solve that for x. Solve that for the inverse. So you get 1 equals x times inverse f of x minus 2, divide by x, 1 on x equals inverse f of x minus 2, and add 2 so that you get 1 on x plus 2 equals the inverse of f of x. And then you found your answer. So that's an alternative process and method that you can use when finding inverse functions. Okay, let's go back down to example 3. Okay, so given that we have f, which has a domain from negative infinity to 2, not including 2, and f of x has rule x squared minus 4x, which is a parabola, find the inverse of f clearly stating its domain. Okay, so again, I like to always think about what things look like. So x squared minus 4x is x times x minus 4, so that's a happy parabola with intercepts at 0 and 4. So it looks something like that. That's 4, but we're only going from negative infinity up to 2, not including 2. That'll be at the turning point. Okay, so we've actually only got that red graph. Okay, so this is 2, whatever, we could work it out, but I'm not really too interested in it right now. Actually, we might, because we'll need it later. So when x equals 2, y is going to be 2 squared minus 4 times 2, so that's 4 minus 8, so negative 4. Okay. So the red graph is our function, f of x, and we want to find f to the negative 1 of x and clearly state its domain. Okay, so we're going to first of all let f of y equal x, or x equal f of y, it's the same thing. So we're going to have y squared minus 4y equals x, and we want to make y the subject. So here we've got y in 2 different places. Okay, so the only way we're going to be able to rearrange to get y on its own is to rewrite the quadratic expression on the left into turning point form, which is a version where we only have y at 1y. Okay, so I'm going to complete the square on the left hand side to get it into turning point form. So half of negative 4 is negative 2 squared is plus 4, and you can either add and take it away on the same side. okay? Or instead, you could add it to both sides. Either way, you're keeping the equation balanced. It doesn't matter how you choose to do it, okay? I tend to always do this. I just do it the same way every time. But if you'd rather add 4 to both sides to complete the square, that's perfectly fine. So these first 3 terms, they are your perfect square. That is y minus 2 all squared, and then you've got the takeaway 4, which equals x. So we're trying to make y the subject, and now what we've done by completing the square is create an equation where we just have y in one place. So we can now do the same thing to both sides until we get y on its own. So we're going to add 4 to both sides. So y minus 2 all squared equals x plus 4. We're going to take the square root of both sides, and it'll be plus minus square root, always. And then y is going to be 2 plus or minus the square root of x plus 4. Now, with the plus and minus, that's not a function, okay? But as part of the rearrangement in solving this equation to make y the subject, we must consider both the positive and negative. Now you want to think about your original function and think about, what you know about the inverse to decide which of the square roots do you need for this particular function, okay? So what we know here is that the domain of f is from negative infinity to 2, and the range of f is from, now that we've worked out that, it's from negative 4 to infinity. Now remember, these will switch around for the inverse. So the domain of the inverse will be from negative 4 to infinity. The range of the inverse will be from negative infinity up to 2, okay? So if you've got a negative range, essentially, you're going to be looking at, when you take a parabola and you take its inverse, you get this sideways parabola, okay? Now, in terms of mirroring in the line y equals x, there's our line y equals x through the middle there, okay? The left-hand side of the parabola mirrors to give the bottom half of the square root. So if you've got the left-hand half of a parabola, you're going to have the negative square root, okay? So this will be x equals negative root x. Okay, if you had, y equals negative root x, if you had y equals x squared where x is less than 0. Okay, or less than or equal to 0, it doesn't really matter. If you started with the positive half, the right-hand half of the parabola, its inverse will be the top half of the square root, the positive square root. Okay, so in this question here, we started with the left-hand half of the parabola, and so therefore the inverse function is going to be the bottom square root, the negative square root. So when we state our function, so y is equal to that, but when we actually do the answering the question the step, which is to state the inverse function, it must be a function, and so we only want one of these, and we think that through, and we decide that we need the negative square root in this instance, okay? And then we also want to state the domain of the inverse, which we know will be the range of the original, which we have already worked out, is going to be negative 4 to infinity. Not inclusive, because the turning point is not included in the domain. Just check we've answered the question. Find f to negative 1, clearly stating its domain. So we have found f to negative 1 and clearly stated its domain. Okay, so making sure that we answer the question. Let's just get rid of that rough scribble for now. Okay, example 4, the final example here. Express x plus 4 over x plus 1 in the form a over x plus b plus c, and hence find the inverse of the function f of x equals x plus 4 over x plus 1. So before we get started on what it's actually asking, let's just be clear that if we wanted to find the inverse of that, we would be letting f of y equals x, and we'd get y plus 4 on y plus 1 equals x. And this would get hard to rearrange. It's not impossible, but it would get hard to rearrange because we've got two y's. So if we can, before we try to find the inverse function, take something of this form and rearrange it into this form, where in this form you've got two x's, which will become two y's when you're trying to find the inverse. Here you've only got one x, okay? So the advantage in reformatting it into this form first will then make it much easier when we want to try and find the inverse function, okay? So this is a kind of, technically this is sort of partial fractions, which if you've done some specialist maths, this would be familiar to you. But in its simplest form, this is really not very complicated, and I try not to overcomplicate the things here. The biggest issue that we want to understand is our original function has an x in the numerator and the function we're trying to get to has no x's in the numerator. So we want to be able to cancel down x out of the numerator. Now, the only way we can cancel out x is if we have common factors, and given that there's no common factors in the denominator, we're going to need to have a whole of x plus 1 in the numerator so that we can cancel it out. So we create that. Sorry. Okay, so what we do is we force it up there. Okay, I want the denominator to be in the numerator so that I can cancel down, so I'm just going to write it in the numerator. And then I'm going to work out what has to go around it to make it work. Now, sometimes you might have to put a number out here. You might need 2 out here if there was a 2x plus 4 up here, but we don't need any number there because we've only got 1x, and we've already got 1x there. But we've now got x plus 1 in the numerator, and we want it has to be equal to x plus 4, so we're just going to write it like that. So x plus 4 is the same as x plus 1 plus 3. But the advantage here is that now we've got these are the same. Okay. So our next step is now to split up our fraction. This can be written as 2 separate fractions, x plus 1 over x plus 1 plus 3 over x plus 1. That's how common denominators work. You add them together, you get that. So therefore you can do that in reverse to get that. And the advantage here is that in this fraction, the denominator and numerator cancel out to leave 1 over 1, which is 1, plus 3 over x plus 1. So let's just mirror the form that we were asked for. So it is 3 over x plus 1 plus 1. Okay. So what we've now learnt is that f of x, which is equal to x plus 4 over x plus 1, is also equal to 3 over x plus 1 plus 1, which is going to be a much more helpful form with which to find the inverse, which is the second part of the function. We've got this word hence happening here, which is a really important instruction in methods, meaning once you've done the first part, use it to help you with the second part. And when you see the word hence, it actually means you must use what you just did. Okay? If it says hence or otherwise, it's just a hint to you. What you've just done might be helpful, but you can do it in another way if you prefer. If it says hence, you must use what you've just found. Okay? So for the inverse, I'm going to let f of y equal x, but I'm going to use this second version of f of x. So I'm going to write that as 3 over y plus 1 equals x. And now we just want to make y the subject, so I'm going to take away 1 from both sides. I'm going to multiply by y plus 1 to get rid of the fractions. I'm going to divide by x minus 1. And I'm going to take away 1. Okay, we want to answer our question, so therefore our inverse function is 3 over x minus 1 minus 1. Let's think about domain, let's think about the original function. So we didn't have any restrictions here at all. So our original function was this, which is a hyperbola translated left by 1 and up by 1. So it would have been x equals negative 1. And y equals 1. I would have done something like that. So the domain of f would have been all real numbers except for negative 1. And the range of f would be all real numbers except for positive 1. And so the domain of the inverse is going to be the same as the range of the original, so all real numbers except for 1. So domain of the inverse is range of the original, which is all the real numbers except for 1. And that marries with this, the domain of that function would indeed be all real numbers except for 1. In fact, it's not a restricted domain in this case, it is just the implied domain. Okay, so quite a lot of practice around inverse functions from exercise 1F.